Hello, hello, guys. Am I audible clearly? Just write in the chat if I'm audible. Hello, guys. Is anybody there or not? I see some viewers. So just write us in the chat if you can hear me well. Hello, Prince. Good morning. Hi, Arpit. Hello, Pradeep. Okay. Good morning, everyone. I hope you are all fresh. I hope you all had breakfast. So, yeah, welcome to today's PCD of Leetcode Weekly Contest 447. And we'll discuss all the four problems today. But so before we start, I will tell you about TLE's CP sheet, right? So this sheet contains 31 handpicked problems from all the ratings from 800 up to 1900, and these problems are carefully picked such that each problem teaches a unique idea, right? Also, our sheet has been upgraded with an interface where you can actually connect your this sheet with your CF account. So it will automatically fetch all the problems that you have already solved. Also, every week 7 to 8 solutions will be uploaded on YouTube, so you won't have to go looking for them. By now, we are till here, okay, and yeah, and furthermore, there is a leaderboard where you can see your rank and all according to how many problems you have solved in the CP sheet. And yeah, also we have a discuss section, so where you can discuss the problems as you can see. So, anyways, this was about the CP sheet. Now let's start with the PCD now. Okay. So the first problem today was count covered buildings. You are given a positive integer n, representing an n by n city. You are also given a 2D grid buildings, where buildings of I is equal to xy, which denotes a unique building located at the coordinates x, y. A building is covered if there is at least one building in all four directions, left, right, above, and below. Return the number of covered buildings. Okay, so we have is a 2D plane, right? We have a 2D plane, and on that 2D plane, like, we have some buildings, right? So let's say a building is right here on this coordinate, then a building is right here, then there's a building here, let's say, and there is a building here. Okay, so they want us to return the number of covered buildings, and covered buildings means that there should be at least one building in each of the four directions, that is above, below, left, and right. So for example, if I want to check this building, then there has to be a building above, left, below, and right. So as you can see there is a building above, and above and left there are buildings, but there are no building to the bottom and to the right. So therefore this particular building is not a covered building, and all these four buildings in this diagram are not covered buildings. Okay, that is the thing here, right here. So we have to count the number of covered buildings, right? So how can we actually do that? So first of all, let's try to discuss an O of n square solution. Like, here the number of buildings, like buildings dot length, can be up to 10 to the power 5, right? 10 to the power 5. So we cannot actually do O of n square, but I will show you how to do that first. Okay, and then we'll build upon that. So let's say you want to check, let's just iterate over all the buildings. Like, you will check this building, you will check this building, check this building, and check this building, and out of them, check for everyone that is it covered or not. And if it is covered, then you'll just add it to your answer. Okay, and how do we check if it is covered? We'll just check that, let's say that this is at point 3 comma 5 or something. Okay, this is at 3 comma 5. So just check that, just iterate. Like, let's say you want to check for this. So now what you can do is just iterate over all the other buildings. Okay, like let's say this building is 4 comma 5, this building is wait, yeah, okay, 4 comma 5, this building is 3 comma 2, and this building is 4 comma 2. Okay, so let's say you want to check this one, then you will iterate over all the other buildings, like these three buildings you will iterate on. Okay, so let's say you check this one. So as you can see that the y coordinate of these two buildings are same, and the x coordinate of this building is more than the y coordinate of this building. Okay, like let's say I am currently checking for xi yi, like this building I am checking that is it covered or not, and I am iterating over all the other buildings, right? So currently if I am at the building xj yj, then if my yj is equal to yi, right, and my xj is greater than xi, what does that mean, guys? That means that this jth building is on the right of this ith building, right? So basically we have found one building which is to the right, so we'll mark right as true. Correct. Then one more, like we'll keep iterating, and let's say if my x coordinate is same, like xi equals to xj, and let's say my yi is greater than, or let's say my yj is greater than my yi. So in that case I'll say that this jth building is above, is up to with respect to the ith building, so we'll mark the up also as true. So that's what we can just do, is like we can iterate over all of these other buildings and just mark these variables as true, like whether or not we have found a building to the right, or a building to the up, or a building to the down. So down means that xi should be equal to xj, and yi should be greater than yj, right? So in this case you will mark down as true. So this is your O of n square approach, right? But it will not pass unfortunately because the constraints are up to 10 to the power 5. So what you actually need to do is optimize this efficiently. So okay, let's think about this. The thing that you can actually exploit is the fact that, let's say that I want to find something to the right, like let's say I am currently at this xi okay, and I want to find out whether or not there is a building to its right. Okay, like I want to find out if there's a building to its right or not. So in if there's a building to right, like if there's a building to its right, then its y coordinate has to be same, like yj is equal to yi. So basically I know that building's y coordinate, I know a building y coordinate, and also I know that its x coordinate must be at least like greater than xi, right? So I know the y coordinate, and I know that xj greater than xi. So actually if I store all the points according to the y coordinates, like for example if I just store the points like this, like in a table I store kind of. Okay, so what I'm actually doing is, see, let's say I store my points like this, like for example these two points have y, sorry, these two points have y coordinate as 5, right? So in my 5 I will store 3 and 4. So what does this mean? That for this y we have these x's, buildings are there on these x coordinates, and for this y equal to 2, for this y2 we have buildings at these x coordinates, right? So let's say I want to find out that is there a building to the right of this 3 comma 5 or not. Okay, then of course if it is to the right, if it is to the right, then that means that yj must be equal to yi, right? So, and we know that yi is 5. So, I want to find another building whose y coordinate is 5 and whose x coordinate is greater than 3, right? So, in this vector, like in this list of x coordinates, like this is the list of the x coordinates whose y coordinate is 5, right? Like this is the list of all the x coordinates in the y equal to 5 line. So in this list, we can search for a number which is greater than my xi. Like since my yi is 5, so in this 5 value list, I'll search for a variable, or I'll search for an x coordinate which is greater than 3. Greater than 3. So for that, I can simply use binary search, because I'll keep them sorted. Like I'll keep this list sorted. So I can simply do binary search. Or we can even make a map. Like we can store a map for 5. Like for example, I just do this, that for y equals to 5, I have these points, and for y equal to 2, I have these points. And then in the map also, I can just use the upper bound function. The upper bound function to find out that is there any element greater than 3. So of course, if I do upper bound on this 5, it will give me this 4. So I'll know that there is a point to the right of it. Okay. So what about left of it? Like if I want that yj, like if I want that building j is left to building I, then what does it mean? Then it means that my yj should be equal to yi, and my xj should be less than xi. So basically, in my 5, let's say I want to let's say if I want to find that for this 3 comma 5, is there something to the left of it? So we'll find out that in my y equal to 5 or list, in my y equal to 5 list, so in this list, is there anything which is less than 3? So to do that, we can just simply do lower bound. Like we can use lower bound. Lower bound will give us the first element which is greater than or equal to 3. So we'll just do minus minus lower bound. So that will give us less than 3. The last element less than 3. And if this lower bound, is turns out to be the begin, like if it turns out to be the first element, then that means there are no elements less than 3. So therefore left doesn't exist. So that's what you can do for right and left. And similarly, if you store the x coordinate also, like if you store a similar set of lists according to x coordinates, like here I stored according to y coordinate, right? Like y coordinate 5 में ये x है, and y coordinate 2 में इतना इतना x's है. So if I just store according to x coordinate as well, like x coordinate 3 में ये y's है. कौन सा y's है? 2 and 5. And x coordinate, in x coordinate 4, I have these y's 2 comma 5. So using these vectors, I can find the up and down also. So what I just have is I have a map for each x coordinate, that what y's are there in that x, and for each y coordinate also I have a map which stores that what x coordinates are there for that y coordinate. So in that, I can just do binary search, and for each point I can find out that whether there are any left, right, up, down in O of log n. O of log n into 4. Like I'll have to search in all the 4 directions, right? Like while searching for the upper one, like while searching for right, I'll do upper bound on the y one. Then searching for the left, I'll do lower bound, and so I'll have to perform 4 operations. So it is O of log n per building. So overall, it is just O of n log n, right? Like I'll just do binary search on that map. Okay. So this is the solution to the first problem. And like before I show the code, does anyone have a doubt in the logic? If anyone has a doubt, then please let me know. Okay, yeah, Ronak says that we can just use min and max element. That also works. That's true. That is also a nice solution. So that will solve the problem in O of n. Like what Ronak is saying is that for every y, like I'm storing a list of the elements, right? Like for this y equal to 5, I'm storing this list of elements 3 and 4, like the x coordinates 3 and 4. But so I'm storing all of the x coordinates in this y coordinate. But what I can just do is store the leftmost and the rightmost x coordinates. So just the minimum and the maximum elements, because like that's it, that's sufficient, right? Like if I just store, like let's say I have many points on a certain y coordinate, like let's say on this y equal to 5 I have so many x coordinates, right? So let's say I want to find out for this point that is there it's right, like is there r and is there l. So what I did was I did upper bound, right? I used upper bound, so that will return me this point. So instead of what I can do is I can just store the coordinate of this point and this point, the minimum and the maximum, and I will know that if my point is in the middle, then of course there will be at least one point to the left of it and to the right of it, right? So that also works. Yes, Madhu, that is the solution here. We can also check for the first and last element. That's what Ronak said and I explained. That is also correct, and that will solve it in O of n. Okay, and my solution will solve it in O of n log n, but both will pass. There is no problem in that. So I hope it is clear to everyone. Just a minute. Okay, yeah. I hope it is clear to everyone. And I'll show you the code now. Okay. So what I'm just doing is that I am iterating on these points. Like, okay, I have my ans equal to 0, which is I am counting the number of covered buildings. Then I have a list of maps. Like I have a vector of map mx and my. So mx of I, like mx of I is the set of all y coordinates for which x is equal to I. Okay. Like my mx of I, like my mx of I is the set of all y coordinates such that x coordinate is I, right? That is the list. Like we are storing a map. Okay. And my similarly, that my of I is all the x coordinates such that y coordinate is I, right? So what I'm doing is iterating over the buildings. X is equal to buildings I0, y is equal to buildings I1, and mx of x comma y plus plus. So like I increase the frequency of this y coordinate inside the x list. Okay. And also my of y comma x plus plus. So I increase the frequency of this x coordinate inside this list of y. Now I just iterate over the buildings. Okay. And in the ith iteration, I want to check that is the ith building covered or not, right? So to check that, what we can do is like, okay, x coordinate, y coordinate of the current building. Now to find out the right or up, like in this case, I am finding out the up. Like in the x coordinate, like the same x coordinate, I am finding upper bound of y. Okay. Then it2 I am storing same x coordinate. I am doing lower bound of y. Then it3 same y coordinate upper bound of x, and it4 same y coordinate lower bound of x. So if these iterators are not end iterator or begin iterator, like if this upper bound is not equal to the end, then we have an element greater than the y. Like if upper bound of y is not equal to the end iterator, then that means that we'll have an element which is greater than y, right? So it1 is not equal to mx of x dot end, and it2 is not equal to mx of x dot begin. So if my lower bound is equal to mx of x dot begin, that means that y is the smallest point. Like y is the smallest point in that x coordinate. So there are no points at the bottom of it or below it. So I don't want that. So I'm just checking that it1 is not the end, it2 is not the begin, it3 is not the end of my of y, and it4 is not the end, begin of my of y. So if both all four of these are satisfied, that means there are all four directions. In all the four directions, we have points. So I'll increase the answer, and then I'll return the answer. Okay, that is the logic here. I hope you understood this. All right. So if anyone has a doubt in the code, then they can ask me right now. Pradeep is saying it is clear. Okay. So I think it is clear to all. So I'll move on to the next problem. Tanuj saying is clear. Okay. So okay, the problem two is given that you are given an integer n representing the number of nodes in a graph labeled from 0 to n minus 1. You are also given an integer array nums of length n sorted in non-decreasing order and an integer max diff. An undirected edge exists between the nodes I and j. If the absolute difference between nums I and nums j is at most max diff, that is, absolute value of nums I minus nums j is less than equal to max diff. You are also given a 2D integer array queries. For each queries, that is ui comma vi, determine whether there exists a path between the nodes ui and vi. Return a boolean array answer is true or false. Okay. So what we have here is that we have been given an array, right? We have been given an array containing sorted elements. Okay. So let's take an example. Like let's say we have 2, 5, 6, 8. 2, 5, 6, and 8. So the thing is that okay, this is my given array and it is always sorted. It is guaranteed that this array is sorted. Okay. Now we have been given queries, and okay, what we have to do is we have to make a graph from this, like a graph with n vertices numbered from 0 to n minus 1. So vertex 0, vertex 1, vertex 2, and vertex 3. Right. In this case, max diff is 2. Sorry. Max diff is equal to 2. This is my parameter. So yeah, what they are saying is that we can make an edge between two nodes if their difference is less than equal to 2, right? So I cannot make an edge between 0 to 1 because the difference between 2 and 5 is not less than equal to 2. So okay, now actually between 2 and 6 also, and between 2 and 8 also, I cannot make an edge. Like between 0 and any other vertex, I cannot make an edge, right? Then from 1 to 2, like I can make an edge from 1 to 2, like between 1 and 2, because this 5 and 6, the difference is less than 2, less than equal to 2. And between 1 and 3, can I make an edge? No, I cannot make an edge because um, this is not less than equal to 2. And between 2 and 3, I can make an edge because 6 and 8, the difference is less than equal to 2, right? So finally, this is my graph. This is my graph, and on this graph, I have to answer the queries that are nodes u and v connected. Like, is it possible to reach node u from node v? Okay, that's what we have to answer. So we can simply use DSU. Like, okay, someone might say, like, someone might think that we can simply create this graph, right? And do a DSU, perform a DSU on it, and answer the queries. But bro, you are wrong. Why? Like because the number of nodes in this case also, it is up to 10 to the power 5. Up to 10 to the power 5 is it? It is. So number of nodes, there is no problem that they can be up to 1e5, right? But when you try to like make the edges, right? Like you will, what you will do is you will iterate over all pairs of nodes I and j. Like ideally, what you will do is that you will do for I equal to 0 to n minus 1, and for j equal to I plus 1 to n minus 1. You will check if nums of I minus nums of j absolute value is less than equal to max diff. So you will check this condition and you will make an edge if that is so. Like you will make an edge in that case. So but this thing, like this approach, as you can see, this is O of n square. Like just creating the entire graph is O of n square. Right? So we cannot actually do that. And actually we cannot even make the graph in better than O of n square, because the graph can contain O of n square edges. Like what I'm saying is that it is possible that between every vertex there is an edge. Like between every pair of two vertices there is an edge. That is also possible. Like let's say my max diff, in this case my max diff was 10, right? Then in that case between all of these vertices there would be an edge. So there would be n square edges. I mean O of n square edges. So you cannot actually make the entire graph. You cannot make the entire graph. You have to somehow answer these queries without constructing the entire graph, right? So how do we actually do that? So let's think about it. How to do that? Okay. So we had the array 2, 5, 6, and 8, right? 2, 5, 6, 8 we had. Now guys, instead of just imagining graph, like instead of imagining that using this array we make a graph, and then we do moves on that graph. So instead of doing that, like instead of imagining that, just imagine that this is your graph. Okay. Like the thing is that there are n positions. Like this is the first position, this is the zeroth position, this is the first position, like index, the first index, the second index, and the third index, right? So and let's say you are at position number 0. So from position 0, where can you go? In one move you can go from 0 to any other element if its difference is less than equal to the max difference, right? This is your actual thing. Like instead of thinking about a graph, we can just think about traveling on this array only. Like instead of traveling on a graph, we can think about traveling on an array. Like see, the queries are what? The queries are given to us that can we reach to v from u? Can we reach to v from u? That is the query in our graph. So actually we can treat the query as in our array only. Like we can say that our queries are of the form that can I reach the index v from the index u. Like okay, there are 4 indexes which are like 4 nodes are there, so we have 4 indexes, and let's say the queries are there. Let's say what queries are there. So queries 0, 1, 0, 2, 1, 3, and 2, 3. So can we reach, so the queries, let's say the first query is 0, 1, right? So they're asking that can we reach 1 through 0? Like can we reach 1 from 0? So can we do that? Like is there any path? Is there any path from which we can do that? So no, in this case it is not possible, because from 0 we cannot move anywhere. So there is no way to move to 1, right? So even for 0 comma 2 also the answer is no. Now for 1 comma 3, like can we move from 1 to 3? Can we move from 1 to 3? So actually directly we cannot move, obviously. Directly we cannot move because the difference is 3. But we can actually jump through 6. Like we can just jump through 6, and then from here to here we can jump. So in 2 moves actually we can go to 8. So the answer to this query, which is 1 comma 3, it is yes. So okay, as now I think you understand that how I am telling you to visualize this problem. That instead of a graph, just think of it like an array only. Like in this array, you want to travel from this index to this index, or from this index to this index, or so on. Like whatever the queries are there, you have to answer them. So how can you travel on the array? Now, one thing to notice is that the array is sorted, right? The array is sorted. So actually, let's say I want to move from a point A to point B. Like in general case, let's say that let's assume this is my array. Assume this is my array, and my maximum difference is given to me, like something k value is it. It is some k value, and this is my array. So let's say I want to move from this point A to this point B. Okay. So guys, what is the best way to do that? What is the best way to do that? Like to ensure that I reach here, if I can. Like what I'm saying is, you can move from here to some other point, if and only if that difference is less than equal to max difference. Less than equal to max difference. So my point is that what you should do is that okay is that you should just travel from here to here, then travel from here to here, then here to here, then here to here, and then here to here. Because as you know that your list is sorted, right? It is sorted. So for example, it might be something like 2, 4, 5, 7, 8, 10, 13, 17, and 18. So let's say this is your array. So if you want to travel from 5 to 17, okay, then you should actually the best way to do that is to travel like this. So in this case, even if your maximum difference, let's say your maximum difference was given to be 4, okay, then you can actually travel from here to here, because here the difference is 2, difference is 1, here the difference is 2, here difference is 3, and here difference is 4, right? So that's how you can travel from A to B. But let's say your maximum difference was only 3. Your maximum difference was only 3. Okay. Then actually you can only travel up till here. Like you actually cannot travel between these two vertices, because here the difference is 4, right? Uh, like between these two vertices, the difference is 4. So that's why you cannot travel from here to here. And since the list is sorted, actually you don't have any way to move from any of these vertices, like to move from any of these vertices to any of these vertices. Like let's say you start from any of these vertices, either here, here, whatever, you won't be able to jump this gap. So of course you can't even jump this gap, right? So that's why if there's a large gap between, so at this point there's a large gap of 4, which is greater than my maximum difference. So I can definitely comment that these two are different components. Like this component, this entire component, and this entire component is my different component. Okay. And so definitely I cannot move from any point in here to any point in here, right? So that's it. Like that's what I got to do. That if I have my array, let's say I just construct an array, just 2, 3, 7, 8, 10, 13, 20, and 23 we have, and 24, let's say. And let's say your max diff for this case is equal to like it is equal to 3 only. Okay, it is equal to 3. So basically you can move between these two, right? You can move between these two. You can move between these these 4 elements, because like you can move from 2 to 3. It is possible to move between 2 to 3, but you cannot move between 3 and 7. So definitely this component is a separate component. you cannot move from here to anywhere between here, like to anywhere here, right? So this is separate. Then 7 to 8 you can move, 8 to 10 you can move, 10 to 13 you can move, but this gap you cannot move. So this is one more separate component. And this gap you can move, and this gap you can move. So this is one more separate component. So these are your three components of your like kind of graph. And you can only move between the two components if there is, if they're like, you can only move between two vertices if they are in the same component. So that's how you will use DSU. Like that's how you can just add edges between adjacent elements, adjacent elements whose difference is less than equal to max difference. Like if my nums of I, like if my nums of I minus nums of I minus 1 is less than equal to max difference, is less than equal to max difference, then I can join I and I minus 1. Okay. So your array will be divided into some contiguous subsegments, and you will not be able to move outside of them. Like you cannot travel from this subsegment to this subsegment because this gap is too large. Okay. So that's how you can just use DSU and add an edge between any two indices such that their difference is less than equal to max difference. I mean two adjacent indices. So at max you will only have n minus 1, like, or O of n edges in this graph that we are making, kind of. So in this DSU you'll only call the join function O of n times, and then you can handle the queries. Right. So yeah, this is the solution. And means if the parent is same for two vertices, then the answer is true. Yes, exactly, Tanuj. If they are in same connected component, like if two vertices are in same component, then their ancestor, not the parent, like in your DSU, when you do find set, like when you do find set of int a, right, then that is the representative representative of that set, right? So if the representative of both the vertices are same, that means they are in the same unit, they are in the same set, and you can say that they are reachable. So the answer is true. Okay, Tanuj. Prince is saying that sorted make this problem solvable. Prince, if the array was not sorted, then also you can solve this. You can just sort the array, right? Like, because the number of nodes don't matter. Like what they are telling you is that in this array, the number of node 0 is 2. I mean, the number on the node 0 is 2, number on the node 1 is 4, number on the node 2 is 5, and so on. So when you are answering the queries, you are checking if these lie in the same component or not, a and b same component or not. But if you didn't have the sorted array, then you could just store the index. Like you could just make a vector of pair and sort the array. And then if you want to answer the queries, you can answer that according to the new vector that you have. Like in your new vector, you will have some contiguous subsegments, and you can simply store the positions, that where did the vertex I go, like after sorting, where did this vertex I go, and simply you can answer the queries according to that. Yeah. Anyways, so I think it is clear to all. So I'll show the code now. So I have this DSU code. This is just standard DSU, and here you can see that I am zoomed in. Yeah. So what we have is, I just resize, like I initialize the DSU, like parent dot resize in si dot assign n comma 1, and parent of I equals to I. So initially they are all disconnected components. Now for int I equal to 0, for int I equal to 0, I less than n minus 1 I plus plus. If nums of I plus 1 minus nums of I is less than equals to max difference, then I can add an edge between those two. So they will be in the same component. And finally, my answer vector, I can just handle the queries. So for auto x in queries, if the find parent of x0 is same as find parent of x1, then ans.pushback true. Otherwise, ans.pushback false. And then we can return the answer. Final vector of Boolean. Okay. That's the solution right here. And I think it should be clear. If the logic is clear, then the solution should also be clear. So yeah. Okay. So now let's move on to the problem number 3. Can we also solve problem 4 like this approach? No, because problem 4 asks for the minimum distance actually. Like this asks that what is the minimum distance between two nodes? Like, but problem 2 asks that is the distance infinity or not, essentially. Like, can we reach from point A to point B? That is what the question 2 is asking. But question 4 is asking that if we can reach from point A to point B, then what is the minimum distance that we have to traverse on the graph? So that you cannot solve it by just DSU. You will have to use some other tricks that I will tell you. Okay. But before that, I will do this problem number 3. Okay. So yeah, this problem 3 we have. Okay, Madhu is asking, can we also use prefix sum for problem 2? Prefix sum, yeah, we can use prefix sum. Like simply, what we can just do is, see, what I did is that I want to divide this into subsegments, right? I want to divide this into subsegments. That means I have some partitions right here. Like let's say this was my array. Like let's say this was my initial array. So I have added a partition between these two numbers. Like between 3 and 7 there's a partition, and between 13 and 20 there's a partition. So if my in my query, if the two numbers are inside the same partition, or I can say that between these two numbers, if there is no partition, then they are connected, they are in the same component, right? But let's say if let's say this is 8, and there is one more query, like my query is this and this. So of course they're in different components, and we can detect that because there is a partition in between these 2 points, right? So what we can just do is we can make an array of where the partitions are there. Like we can make a maybe boolean array or maybe an integer array, and we can store 0 if there's not a partition here, and we can store 1 if there's a partition here. And what we just have to do is count the number of partitions from this index to this index. Like if there's any partition between these two indexes, then the answer is yes, or sorry, the answer is no. Otherwise the answer is yes. And to count the number of partitions between any two indexes, we can use the prefix sum. Right. That's also an approach, but the easier one is DSU. Like the easier one to write is DSU, because in prefix sum one you will have to handle that. What will you call this? Like, will you call this index 0 or index 1? Will you call this 0 or 1? And if you have a query of A index and B index, then in what range will you search for the partition? So you'll have to handle these cases, like these small things in our code. But other than that, this is also a solution, a valid solution. Okay. So yeah, I'll move on to the problem 3. You are given an array of positive integers nums and a positive integer k. A permutation of nums is said to form a divisible concatenation if when you concatenate the decimal representations of the numbers in the order specified by the permutation, the resulting number is divisible by k. Return the lexicographically smallest permutation that forms a divisible concatenation. If no such permutation exists, then return an empty list. A permutation is a rearrangement of all the elements of an array. An array A is lexicographically smaller than array B. Okay, so this is, we already know, like in alphabetical order. We'll consider. So, okay, the question is pretty simple. Okay, like we have been given um, a number k. Okay, less than equal to 10 to the power 5, and we have been given a list of numbers. A list of numbers called nums. Okay, this is my list, right? And what we can do is we can rearrange this list in such a way that after concatenating these numbers in that order, like when I change the order of these numbers, so in the new order, if I try to concatenate those numbers, then my final resulting number is divisible by k. So I need to rearrange it in such a way that my final number is divisible by k. And also I need to ensure that if there are multiple permutations, like if there are multiple arrangements in which I can rearrange my permutation or I can rearrange my array, then I will print out the lexicographically smallest one. Okay, that is the question right here. That given this list of numbers and the number k, we have to rearrange this list of numbers in such a way that the concatenation is divisible by k, and also among all such permutations which are divisible by k, we have to print the smallest one lexicographically. Okay, so how do we actually go about solving this? We first look at the samples, right? So for example, we have 3, 12, 45, so, and k is equal to 5. So basically we want that the final concatenation should be divisible by 5, right? So if we want that it should be divisible by 5, then uh, then what we want is that the last digit either 5 or 0, right? The last digit of the number should be either 5 or 0. So in this list we have only one number that ends in 5 or 0. So this is 45. So of course we have to keep it in the last. Of course we have to keep 45 in the end, and we have to keep 3 and 12. So either we can do 3, 12 and 45, or we can do 12, 3 and 45. So this will create the number 3, 1, 2, 4, 5, and this will create the number 1, 2, 3, 4, 5. So as you can see that this number this number and this number both are divisible by 5, right? So both are valid lists, and this list is actually smaller than this list lexicographically, because the first element, this one is 3 and this one is 12. So lexicographically this list is smaller. All right, so your answer is this: 3, 12, 45. This is our answer, right? So now how do I actually solve this problem? First of all, look at the constraints. Okay, so here k is up to 100 and the numbers are up to 10 to the power 5, and the nums dot length, like the number of numbers, is 13. So 13 is like very unusual. It is a pretty small number. So like usually in CP problems or in DSA problems, we don't get such small numbers except for when the solution is exponential or something, right? So of course, like we are expecting that we might be able to solve this in some exponential time complexity, like maybe in 2 to the power n or something like that, or maybe n factorial. But okay, So let's think about that. So first of actually what we have to do, all we have to do is just rearrange the permutation, right? So how many possible arrangements can be there, rearrangements? So if I have a list of n numbers, then number of possible rearrangements is as n factorial, right? So if we think about just trying all the permutations, then that will take O of n factorial into n time. And why into n? It is just to check that is the concatenation divisible by k or not. So we can check that in O of n time. So this will take n factorial into n. And since the length of numbers can go till 13, up till 13 it can go. So it will be like 13 factorial into 13. So that is actually too big. Like approximately it is 10 to the power 10. You can use a calculator to calculate this. This is 10 to the power 10. So definitely it will not pass. We cannot do this. This is wrong. So we cannot actually iterate over all the permutations. Like complete brute force. Complete brute force will not pass. Brute is failing. That just iterate over all the permutations is failing. Right. So what we actually have to do is kind of a smart brute force. Okay. Like my point is that instead of just completely doing recursion and or something like just completely doing a brute force, what we can do is something like smart brute force, or we can like uh, try to do smart brute force, that is try to do something like dp. Like dp kahan se aaya? I'll explain. Okay, so what we can do is we'll try to solve this problem recursively. Okay, like let's say that I had these three numbers, right? I had these three numbers and I wanted to choose all of them. Like I want that in my final number, all three numbers are there, right? So in my final number, all three numbers must be there. So 3, 12, and 45 must be there, and it must be divisible by k. So the remainder with k must be 0, right? Okay. So now, how do I actually solve this recursively? Like if I want to solve this problem recursively, then how can I actually do that? Let's think about that. Okay. So what I'm saying is that in your final number, you want all these three numbers, and you want that the final number's remainder is 0, right? So okay, if there are three numbers, then either one of these three numbers will be the first one, right? Like let's say if my number is 31245, so I have 3, 12, and 45 in this number. So the first number is 3. The first number I'm calling this 3, right? So in my final number, either 3 will be the first number, or 12 will be the first number, or 45 will be the first number. Okay, that's cool, right? So all right, so either 3 is first number, or 12 is first number, or 45 is the first number, right? So actually what we'll try to do is that just keep all the possibilities, like just try all the possibilities, like just try that what if 3 is the first number. Okay, so we have fixed 3 here, and the remaining number we don't know yet, right? And since we want the remainder of that this number, like our final numbers remainder, we want it to be 0, right? The remainder with 5, we want that to be 0, correct? So when we place 3 at this position, Actually, what do we know? We know that the remaining numbers are 12 and 45, right? 12 and 45 are there as the remaining numbers. So there are 4 digits which are remaining. So my number will look like a 3 and 4 digits. Like if 3 is the first number, so I will try all the possibilities. So the first possibility is that this 3 is the first number, and then I have 4 digits, because of course 4 digits are remaining. So then I have 4 digits, right? And the remainder, like, okay, so I have this number. So now I'll find out that can I make this number using just 12 and 45, right? So I have used up this 3. I have used up this 3, and now I am remaining with 12 and 45, and I want to create this 4 digit number with just 12 and 45. And what do I want the remainder to be? Like, what do I want its remainder to be? See, I want the remainder of this entire number to be 0, right? To be 0, right? And actually, I can write this entire number as, I can write this as 30,000, 3 with 4 zeros plus whatever this is, right? I can write this like that. So I want the remainder of this entire thing to be 0. If I take remainder as 5, like k equal to 5 here, right? So I want that the remainder of this entire number should be 0. And since the remainder of this thing is also 0, that means that, so this thing is 0. So that means that we need the remainder of this thing to also be 0, right? So essentially, what we want is, we want the smallest permutation. Like, what we want is now to make this 4 digit number, like using just 12 and 45, just 12 and 45. I want to make a number such that its remainder is 0. If I can make that number, then I will just put it right here. Okay, so I'll append 3 to the front of it, and that will still have the remainder 0. Like if my uh, this number, like if I'm able to create a number with this 12 and 45 whose remainder is 0, then I can actually place that number right here after this 3. So the final number will also have remainder 0. So I will have one possibility of creating a rearrangement of these numbers to create um, a final number whose remainder is 0 with k. So guys, do you get till here? So actually, what I have essentially what I have done is that um, if I want to make a number using these 3 numbers whose remainder is 0, then what I want is that either 3 is the first digit, or 12 is the first one, or 45 is the first one. So if 3 is the first one, then what I want is, I want to make this number from 12 and 45, and whose remainder should be 0. So essentially what I have done, I have broken down this problem into a smaller subproblem, right? Because initially I wanted to use 3, 12 and 45 to make the remainder 0. And now I want to solve the problem that use 12 and 45 to get the remainder 0, right? So this is my smaller subproblem. Okay, so if I know the answer to this one, then I can actually find out the answer to this one as well. And actually, there is only one possibility. Like, this is one of the possibilities that 3 comes first. Like, one possibility is 3 comes first. Now, another possibility is that 12 comes first. Okay, like if we want to make a number using 3, 12, and 45, whose remainder is 0. So, one possibility also is that 12 comes first and then 3 digits come, right? So if I want that this entire number's remainder is 0, then that means that these three digits remainder also should be 0, because I can write this number as my 12,000 plus these three digits. So if I want this remainder to be 0, then this 12,000 remainder is already 0. So I want this number's remainder also to be 0. So essentially, I want to make a new number with 3 and 45. Like with 3 and 45, I want to make a new number such that whose remainder is 0. So again, I've also boiled down to a smaller subproblem. So okay, either first three can come. So my problem would become this one, or first 12 can come, so my problem would boil down to this one, or first 45 can come and my problem would boil down to this one, right? So if I am getting true, like if it is possible to make if it is possible to solve that sub problem, then I can use that and put that after my first number and solve the bigger sub problem as well. So like there are three possibilities, like either 3 can come first, or 12 can come first, or 45 can come first. So out of these three, if anyone if anyone gives me yes, like if anyone is possible, then I can print that. And if multiple are possible, like what if multiple are possible, like in this case, as you can see, in this case we know that if we try to put 3 as the first one, then I can make, using this 12 and 45, like I can actually solve this problem. Like I can use this 12 and 45 and make it 0. How? I can make this like 1245. I can make 1245 and the remainder will be 0, right? So essentially I can put that 1245 right here, 1245, and this is my final number that I can get. So this is one possibility. And another possibility is that maybe I put 12 here and then I make 345 here. Like to solve this sub problem, I can actually solve it by 345. So what I'm getting is that if I take 3 as the first number, then also I'm getting an answer. And if I take 12 as the first number, then also I'm getting an answer. So what should I take as my first number? So they have told us that they want lexicographically smallest permutation. So the first number, if we have multiple options, then of course we'll choose the one which is the smallest. So of course I will choose this 3. I'll choose this 3 and I'll try to make a permutation using these two numbers with that remainder. Nitin Sharma is asking why sorting. So Nitin Sharma, when did I even say sorting? Like, did you look at my code? Like, I think you just peeked at my code or something, because I never mentioned sorting right here. Up till now, I never mentioned sorting, so I don't understand what you are asking. So can you please clarify when did I say sorting? Okay, so yes, Ayush is correct. Ayush is saying that we can use bit mask. Why? Because basically my problem is what? My problem is that I have to use this 3, 12, and 45 to get the remainder 0. Correct? And I can break it into a smaller sub problem that I want to use 12 and 45 to make this remainder 0. Okay. And I can even break this down into another smaller sub problem that I want to use this 45 to make this remainder 0. So essentially my problem is just dependent on what numbers are there and what's the remainder. Like here, the set of numbers is 3, 12, and 45, and the remainder is 0. So I can break it down into the set is 12 and 45 and the remainder is 0, or the set is 3 and 45 and the remainder is 0. So actually, my sub problem, like my problem can be determined by the subset and the remainder with k. All right, like let me just give you another example. Like let's say, for example, your numbers are there. Let's say what numbers you have. Let's say you have what should I take? Let's say you take 3 and let's say you take, okay, not 3, let's say you take 4, and let's say you take 8. So this is your list of numbers, and your k is given to be 3. Okay, so this is your problem, that you want to use this 4 and 8 to make remainder 0 with 3. You want to use this 4 and 8 to make remainder 0 with 3. So for that, in my final number, either 4 will be there first or 8 will be there first, right? So I'll try keeping 4 first. Okay, so if I have 4 first, then I will have one more digit, because I have only one more digit left in my numbers. So this is one more digit. So what I essentially want is that the remainder of this should be 0 mod 3. This should be 0 mod 3, and I can write this as 40 plus this number should be 0 mod 3. So the remainder of 40 is actually 1, right? So I want that this blank should be 2. This should be 2, so that their sum is 0, right? So my problem of 48 comma 0 actually boils down to 8 comma remainder is 2. Like I want to make a number using this set whose remainder is 0, that is equivalent to making a number with this set whose remainder is 2, right? So that's how my problem can be determined by the subset, by the set of numbers and the remainder, right? So this is what my problem boils down to, that my problem can be determined by the subset and the remainder with k. So subset, like to store subsets, we can actually use bit mask, right? That is one well-known method that you can use. So to store the subset, like what subset are we currently looking for the answer. So like to answer that, we can simply store its bit mask. Like for example, here we have 3, 12, and 45. We have 3, 12, and 45. So we have basically three numbers. So in our final number, we want that all three of them should be there, right? Okay, I'll call this index 0, this is index 1, this is index 2, right? So my point is that all of these three indices should be there in your final answer. So you want your subset is 111, like your bit mask is 111, like this is 2 to the power 0th bit, 2 to the power 0 bit, 2 to the power 1 bit, and 2 to the power 2 bit, right? So you want 111, and also the remainder that you want is 0, right? So you can break this down into recursively. You can break this into three problems. Like, if you have three set bits, that means you have three numbers in your number. So either one of them can be the first number. So either this 2 to the power 0, that means either the 3 can be the first number. So in that case, I will say that 110 and the remainder 0. I'll solve this. So 3 is the first number. 3 is the first number. Or I can say that 12 is the first number. So 12, and here the problem is like 101 and the remainder should be 0. And here the problem is 4 5 dash dash dash, and this is the mask is 0 0 1 1 and the remainder we want is 0. So if either one of these answers is true, like if this answer is not false, then I'll take this one because I want the smallest one. So I'll choose this 3 as my first number, and then whatever comes after that, we'll take that. So yeah, my DP states are just the bit mask, like the state of my DP, like the state of my sub problem is my mask, that which numbers do I have to use, and the um the remainder of the final number that I want, modulo k. So now how do I transition? My state is this mask comma remainder. So how many states are there actually? This mask will have 2 to the power n possibilities, right? And remainder has k possibilities. Like a number can have k different remainders with the number k. Like the remainder can be 0, the remainder can be 1, it can be 2, and up to the remainder can be up to k minus 1. So there are k possibilities. So we simply have 2 to the power n into k states, right? So what do we have to ensure? Like, okay, this is my state, and now how do I transition? Now actually, I was doing it like recursively, right? That first I am trying to solve the subproblem of 111 comma 0, and to solve that I am trying to solve this 110 comma 0. Oh, sorry, 110 comma 0, and I'm trying to solve 101 comma 0, and I'm trying to solve 01 comma 0. And to solve these ones, I will again try to solve this and this and this. So instead of doing it recursively, actually I like to do DP iteratively. Okay, so I am doing bottom up transitions instead of top down. So essentially, instead of saying that, like, if I want to make 3 12 and 45, if I want to make a number using these numbers, so instead of putting 3 and solving for this subproblem, I will first solve for this subproblem and then try to put 3 here. Okay, that is my approach for this problem. So I'll try to solve the smaller subproblem first, and using them I can solve the bigger ones, right? So what I'll do is, this is my mass, this is my remainder. So my base case is what? My base case is that if I don't use any numbers, like if I don't use any numbers, so my mask is 0, like my subset is empty. So my 2 to the power 0 bit is 0, 2 to the power 1 bit is 0, and 2 to the power 2 bit is 0, because I did not take any of these numbers, right? So my DP of 0 comma 0, it is true. Like it is possible to make this remainder 0, because if we don't take anything, then the number is nothing, like the number is 0 essentially. So the remainder 0 can be possible, and initially all the other DPs are false, right? Now let's say currently we are at some DP ij, we are at some DP I comma j. So what does it mean? That if DP ij is true, dpij is true, that means that using this mask of I, like let's say this I is here is 10010. So using this second and fifth numbers, we are able to make a remainder of j. That is what dpij equals to true means, right? So now into this, like see, we basically have inserted two numbers. Like we have inserted this number and this number. So we currently have, let's say, a 4-digit number. Okay. So whose remainder is j? Like whose remainder is this j? So this number's remainder is j. Right. Now what can I do with this state? I can actually insert any number to the front of it. Like any number which is not there. Like either this number or this number or this number. I can insert any of them to the start of here. To the start of this. Like to the start of this number. So let's say I insert this number. Let's say I insert this number to here. So essentially I am transitioning from I comma j. Okay. So essentially I'm transitioning from 10010 comma j to 10011 comma my new remainder. New remainder, like after I insert a number here, I can easily calculate my new remainder. Why? Because I can just calculate it like the remainder for this part. Like I can simply write this as separately. Like let's say there is some number x written here, so I can write this like x 0000 plus that number for these two. So I can find the new remainder. Like this is my new number, and I can find the new remainder, which is this remainder plus the remainder of this thing. Okay, so which is the remainder of x, or basically x mod k multiplied by 10,000 mod k 10,000 mod k plus j. So this is, and this entire thing taken mod k. So this is my new remainder. This is my new remainder. So I can transition from this state to this state. Like if I had just these two numbers inserted, so I can insert one more, that is this one. So it will become this one. So if this was true, if this state was true, then I can push this true to this state also. Like I can make this state true also. Okay. Also I can, like from this state, I can also reach to this state, like 10110 comma new remainder. Like I can simply insert this number also. Like I have simply inserted this number onto the first one. So my dp state is this one, and this will also become true. So that's why I can use push dp. That's how I can use push dp, and I will know that how many states can I make, like how many subproblems. The answer is true. So if finally if my dp of 11111 comma 0, so finally if I can use all the numbers and the remainder is 0, if that is true, then I can say that it is possible to make, like, it is possible to rearrange those numbers such that the remainder is 0, such that it is divisible by k. So I will say that. So that's how I can find out that whether there exists a solution or not. Now what we just got to do is we have to just do dp reconstruction. dp reconstruction, right? Like we have just did our push dp right now, and what we can just do now is dp reconstruction. And how we can do that? We can simply do it like just store that from which state did we come to this state. Like for example, if I am coming from 10010 to 10011 and I'm marking it true, then I'll also store that I came to this state from this state. Like basically, I'll store the parent. I'll store the parent of this, right? So to generate my answer, to reconstruct my answer, I will check that from which state did I come to this one. Like from which state did I come to this state, right? So either it will be yeah. So to this state, either we would have come by either by 11110 or 11101 or by 11011 or by 10111 or by 01111. So out of these five states, like from wherever I have come to this state, that will be true. That will be true. So let's say that if I have come from this state, that means that I did not have this first number in my set, and now I have the first number in my set. That means that the last number that I added is this number, the 2 to the power 0 bit. That means the first number in the array I just added to my answer. So that is my first number in my answer, and again I will find out that that from where did I come to this, like from which state do I come to this state, did I come to this state. So let's say I came to this state from this state 10110. So that means that while coming from here to here, I must have appended this third number or like fourth number, like 2 to the power 3 bit. So the fourth number onto my number, right? So that's what you gotta do. But now I have to also ensure. So okay, see till now what we have solved is we have calculated the DP, right? Like we have just calculated the DP, that is my answer true or false. For all the possible states, I have calculated that is my answer true or false, right? So if my DP of 11111 comma 0 is true, then I can possibly make a permutation, and if it is false, then there is no way to make a permutation, and I'll return the empty vector. Like if you can see that if not DP ij, so I have initialized this inj by 11111 and j is 0. So if dp of I comma j, that is dp of 11111 comma 0 is false, then I'll return vector of int, so empty vector. So that's what I have solved till now, and if it is true, then I can do that, and I have to reconstruct it, right? I have to reconstruct the permutation. But now I have to also ensure that if there are multiple possible reconstructions, I have to choose the smallest one, the lexicography smallest one. So for example, if we can come to this state from this state and from this state, okay, like let's say that this one is also true and this one is also true, so we could come even from this state or from this state. So which one should we choose? That is the question. So to choose this one, we can simply choose that one in which we inserted the smaller number. Like see, in this one we inserted a2, right? Because this is the 2 to the power 1th bit, which was not set, but now it is set. So while moving from here to here, we inserted this a2 number to the first of our list, to the starting of our list. And from if I transition from this state to this state, then I have inserted actually my a1 to the starting of my list. So which one should I choose? Like should I come from this state or should I come from this state? Coming from both states will give me a number which is divisible by k, but I want the smaller possible value, right? I want the smaller possible lexicographic list. So I should choose the smaller number. Like if a1 is smaller, then I'll choose smaller this one, and if a2 is smaller, then I'll choose this one. Okay, so that's how we can choose. And actually, to help us do that, we'll sort those numbers. Like in our input array is initially not given to be sorted, right? Our input array is not guaranteed to be sorted. So what we'll do is we will, for our convenience, just sort the array. Okay. So when I sort the array, then that would mean that if I have two options, that either I can come from this state or from this state. So either I can insert a1 or a2 to my beginning. So what would I want is that I would want to insert my a1 to the beginning, because definitely a1 is smaller than a2, because I have sorted my array. So initially, if I sort the array, then I can say that I will always insert a1 if I can do that. If I can insert a1, then I will always insert a1, right? So my parent of this 1 1 1 1 1 comma 0 will be this state and not this state. So I have to ensure that my parent of this state is this state and not this state. And how am I am doing that? Actually, it happens naturally only. Okay, like what I'm just doing is that in my code, okay, like I'll just show you my code. In my code, what I have, wait, yeah. So in my code, what I was doing is that I'm iterating over this, like nums dot size. Like as you can see that I am iterating from this 0 to 2 to the power n minus 1. Okay, and I am pushing their dp. So like I'm iterating in this order. Like first I am, okay, so let's say I have these 5 states, right? So what I'm doing is I'm iterating over these states from 0 to 2 to the power n minus 1, and I am pushing that state onto the further one. So like if I'm at dpij, and if dpij is true, then I am pushing this dpij onto this state. I'll explain what this means. I'll explain how I got this. But what I'm essentially doing is I'm iterating over those states in the order from 0 to 2 to the power n minus 1. Okay. And I am pushing that, and I'm making the parent. I'm making the parent as true. Like what I am doing is I am pushing this state and I'm making the parent. So guys, so let's say my final answer is 1 1 1 1 1, right? So I could have come to this using 5 states, like either from 1 1 1 1 0, or I could come from 1 1 1 0 1, or I could come from 1 1 0 1 1, or I could come from 1 0 1 1 1, or I could come from 0 1 1 1 1. So these are the 5 states from which it is possible to come to this state, right? So let's say if it is possible from all of them, like let's say that the answer to all of these states is a yes. Okay. If the answer to all of these states is a yes, then of course I would like to come from this state. Like I would prefer to come from this state, because in this state I'm inserting a0, right? And a0 is the smallest number. So I would prefer to come from this state. And what I have done in my for loop is that whenever I can push my true, like whenever I can push my true value to my parent, like like what is doing, like first, out of these five values, out of these five values, I am going from the smaller to the larger. So the smallest one is this, the smallest one is this, and second smallest is this, the third smallest is this, the fourth smallest is this, and the largest one is this. So I will first go to this state, then I'll push my true onto here, and I'll make my parent of this thing as my this state. Then if this one is true, then again I'll push this true onto here, and I'll make this parent as this thing. And let's say this is false, so I will not push that. Then let's say this one is false, so I'll not push that. And let's say this one is also true. If this one is true, then I'll push this true onto my this, and I'll make the parent of this state as this state. So finally, my parent actually became this one. Automatically, my parent became this one, in which the lowest bit is unset. Like out of all these five states, my parent actually automatically became the highest mask, which corresponds to the lowest number being inserted. So that's what I can do. Like after I sorted the nums vector, I know that I prefer to come from this state. Like let's say that this one is true, this one is true, this one is false, this one is false, and this one is true. So I can come from three states, either this or this or this. But actually, since I have sorted, I prefer to come from this state, because in this state, my first number is the smallest. Like in this state, I am inserting a0. In this state, I'm inserting a1, and in this state, I'm inserting actually a4. So since I know that my a0 is the smallest possible among these three, so I'll try to come from this state. So this is my first preference. So when I'm iterating in my DP, I am first pushing my DP from this one, then I'm pushing from this one. Actually here it is false, so it doesn't matter. Then I'll push from this one. No, so like it is false, so I will not push that. Then this one is true, so I'll push this DP onto this state, and I'll make the parent as this one, and I'll make this DP onto this state, and I'll make the parent as this one. So at the end, if you see, the last parent was like the finally the parent of this state has become this one, the highest mask. Okay. So automatically my code handles. And like if you guys don't understand the intuition of this, you can simply take the minimum of all. Like you can like what you can do is you can just store all the transitions. Like you can just store all the possible transitions that you can come from. Like you can come from here, you can come from here, and you can come from here. And what you can do is just store all of those, and just take that one in which you are adding the minimum possible number. Okay, you can do that also, but that happens automatically in my code, right? So in my code, what I'm doing is I am just sorting the array. I have just sorted the array. Okay, Ash is asking, what if nums is 2 comma 10 and k is 2? So Ash, I think you would think that the answer is 102, right? Ash, are you asking that? Like, Ash, do you think that the answer is 102? So Ash is not responding, but and actually the answer is not 102. Like if the list given to us is 10 comma 2, so we have two options, either 10 2 or 2 10, right? So actually in this case, the answer is 210. Okay, like in our problem, they are saying that we have to print the lexicographically smallest permutation. We have to print the lexicographically smallest permutation when considered as a list of integers. So like these are my two lists. One list is 10 comma 2, other list is 2 comma 10. So this 10 is greater than this 2, right? Therefore, this is smaller one, and this is my answer. So that's what you have to actually report. And that's why I am taking the smallest number first. Like I'm trying to take the smallest number first. Okay. If last number is inserted, how smallest? So I'm trying very hard to understand your question, but I'm very sorry that I'm not able to understand what you're asking. So either you can type in Hindi, or you can type in full sentences if possible. Wait, let me just try to. Okay, you got it. Okay, so I'll show the code actually. So what I am just doing is that from dpij, the answer would be 210, but the smaller is 102. Yeah, but the smaller first number is 2. Okay, the smaller first number is 2. So like, if we want to make the answer using 10 comma 2, then um, we have two options. Either we can keep 2 as the first number, or we can keep 10 as the first number. So I am saying that you should keep 2 as the first number. I am not saying that 102 is smaller, so you should keep 102 as your answer. So Ash, like, why the smallest number is 102? That is right. But what's your point? I never said that you will take 102. And the answer is also not 102. So what is 102? My point is that if nums is 2 and 10 and k is 2, then in that case the answer is 2 comma 10. In that case the answer is 2 comma 10. Okay. And my algorithm also gives 2 comma 10, because I will try to keep the smaller number in the first position. No, the answer is 2 comma 10. Nitin is asking, what if the problem said lexicographically order by characters? Then that problem is a very nice problem, and like it is a completely different problem. Like I don't actually know how to solve it right now. Like I need to think about it, but on the top of my head, I don't actually know how to solve it. So Ash, actually, they are asking that what is the lexicographically smallest permutation when considered as a list of integers. So you have to consider it a list of integers and minimize that list. So to compare two lists, like to compare 2 comma 10 and 10 comma 2, the smaller one is 2 comma 10. So you will return that. So Ash, that's why the answer is 2 comma 10. Anyways, so actually before I show the code, I will tell you, like, I will try to give a brief dry run on a test case. Okay, so let's say I have 286, or let's say I have 2 8, I have 2 4 and 6. Like, this is my list of numbers. My nums is this. Okay, and my k is equal to 4. All right, so what I was doing is that I am making a dp. I am making a dp which has one state as my Like, okay, you will see. So like, let's try to make the DP table for this. To understand the solution better, I'll try run the solution on this test case. Okay. Yeah. So let's say 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 1 1 0 and 1 1 1. So these are the possible bit masks. And what are the possible like remainders with k equal to 4? There are four possible remainders, right? So there are four possible remainders. Either remainder can be 0, or remainder can be 1, or remainder can be 2, or remainder can be 3. Okay. So initially, this entire DP table, this entire DP table is false. All right. Except for the first one. So this is true. And all the other ones are false. I'm not writing the false ones. I'm only writing the true ones. So currently, if we want 0 0 0, like if we have 0 0 0, then um, the answer is true, like for 0, because if we have an empty set, it's the number is 0, so the remainder is 0, right? So from this 0 0 0, where can we actually go? Like, where can we go? We can go to 0 0 1, we can go to 1 0 0, or we can go to 1 1, sorry, or we can go to 0 1 0. Like, either in this number we can insert 6, or we can insert 4, or we can insert 2 in the starting. So if we insert 4, like, or let's say we insert 2, then we'll go to this state. So this state will also be true. Actually, no, remainder will be 2, right? So if the remainder is 0, then if I insert 2 at the starting, right, then the remainder will become 2. So this is my in this state, I'll mark as true, right? So I'll mark that this state parent is this state, or I'll use a different color pen. So what I am saying is, from this 0 0 0, either we can go to 1 0 0, or 0 0 1 0, or 0 0 1. So let's go to 1 0 0 first. So the remainder would be 2, right? The remainder would be 2. So this 1 0 0 comma 2, the answer is true. And we have come from, hey, why does it happen so often? Like, why am I not able to change the pen? Does anyone know? I ask this in every PCD, and no one knows for some reason. But okay. So what I have here is the DP table. So from 0 0 0 we can go to 1 0 0. So we have this, right? And actually, I have messed up a bit, because this is your, like, if we have sorted this, like if we have sorted this array, so this is your zeros position, this is first position, this is second position, right? So this bit is 2 to the power 0 bit, this is 2 to the power 1th bit, and this is 2 to the power 2th bit, right? So the order is kind of messed up here, because uh, after 0 0 0, this 1 0 0 should come, because the 2 to the power 0th bit is this one, right? So that's why just assume that I have written the numbers in reverse. Okay, like just assume that this is 6642. Like, this is the index 2, this is the index 1, this is the index 0. Okay, so now it works out. So from this 0 0 0, we can go to 0 0 1, right? What I am saying is, from this 0 0 0, we can go to this 001 after inserting 2. Right. So basically, I'll write a true here and I'll make an arrow here that we came from this state. Okay. Also from 000, I mean, sorry, the remainder will be 2, right? If I insert a 2, then the remainder will be 2. So from 0, from this 000 comma 0, we can go to 001 comma 2 by inserting a 2. So this is true. Then from 000 comma 0, if I insert a 4, then the remainder mod 4 will still remain 0. So I can go to this state. So it will be true. And if I insert 6, then I have gone to the state of 100 comma 2. The remainder is 2. Okay. So I have dealt with this state. Now I'll go to this state. Like, let's push this state. So I have already inserted this 2. So either I can insert 4 or I can insert 6. So if I insert 4, then it would be 42, right? So the remainder would still remain 2. So from this state, we can actually go to this state, true. Or I can insert 6. So it will become 62. So the remainder is still 2. So from this state, we can go to this 101 also. So this is true. Right. Now from this state, where can we go? From this state, if I insert 2, then it would be 24. So the remainder is 0. So I can go to this state. And if I insert a 6, so it would be 64. So the remainder is still 0. So I can go to this state, true. Right. And so on, you can calculate, like so on, you will do the DP. And finally, you will see that here you have a true. Okay. And you can backtrack. This is the idea of this DP. So what I have done is I have sorted this vector. Okay. And of course, if k equals to 1, then anything that I make will be divisible. So of course, I'll just make the sorted permutation, because that will be the smallest permutation. So I'll sort the nums to begin. Actually, I have already done that. Okay. If k equal to 1, then return nums. Now I have my DP. So as you can see that, right. So in this DP of ij, I am iterating. For int I equal to 0, I less than 2 to the power nums dot size minus 1, I plus plus. And for DP and for j equal to 0, j less than k, j plus plus. If DP of ij is false, then continue. Because if it is false, then of course we won't push it. And if it is true, if the DP is true, then we can push it. Like whatever bits are not set right now, whatever bits are not set, we can set them. So I'm iterating over the bits like that. What I'm doing is, for int u equal to 0, u less than nums dot size u plus plus. And if already that bit is set, if already the uth bit is set in my I, that means I already have it in my set. So I cannot insert it again. So I will continue. Like I won't do that. And otherwise, I have not inserted this u into my set yet. So I'll insert it. So my new mask will become i's or 2 to the power u, right? And my new remainder will be this thing. Okay. My new remainder is this thing. So and what is this thing? This is just j, like the initial remainder, plus 10 to the power, like 10 to the power of number of digits in this I. Number of digits in this I, like total length of I, and 10 to the power that multiplied by the u. See, what I'm doing is that, let's say I have a remainder, like I already have some number that is j, like the remainder is j, and I insert, like, and the number of digits is 5 right here. There are 5 number of digits. right? So if I insert, let's say I insert 26 right here, I insert one more number 26, then what is the new remainder of this number? I want to calculate that, right? So to do that, I can just say that it is j plus 26 into 10 to the power 5 ka remainder. So I have already pre-computed all the powers of 10, and also I have already pre-computed the number of digits in each set. So I want that 10 to the power, like PO is the power, so 10 to the power of total number of digits in the set I, right, into the number. So what I'm doing is 26, 26 into 10 to the power 10 to the power of 5 and plus j. So this is my new remainder. So my new mask and my new remainder, I will set it to be true. I will set that to true, and I'll update the parent. Like I'll update that I have come to this state from I comma j. So I'll update my parent. So for each DP which is true, I know that I have come there from which state, right? So now I'll just reconstruct the answer. Like what I'll do is I'll first try to zoom out this. Yeah, this is messed up. Any idea how do I? Why is total length declared? Because see, let's say I am currently at the state I comma j, right? And I want to go to the state I or 2 to the power u and new remainder. Like I currently have the bit mask I. Like let's say this is 10110, and now I want to insert another bit. So let's say I want to insert this 2 to the power 0. That is, I want to insert a0. So essentially, if I have this number right here, and I'm inserting a naught right here, I'm inserting a naught, right? So what is the new remainder? Like if the remainder of this part is j, then what is the new remainder of this entire total number? That's what I need to calculate, right? So I can actually write this like, I can write this as a0 into 10 to the power of total length of I, total length of the subset of I, plus j. I can write this, right? Like basically a0 0 plus j, like 5 zeros, because there are 5 digits already in my number. Already there are 5 digits in my number, and I'm inserting a0. So therefore the total length is defined. So I can write this my new remainder. This is my new remainder, and I'll update that. Okay. But for now, the problem is, how do I, like, nothing is working legit. Maybe I'll move to a different, well, wait. Okay, finally. So I'll not zoom in that much. Yeah. So what I had done is, if I'm at dp I comma j, I have updated, like if dpij is true, then I have pushed it to all the bits, like all the bits that are not set. I am trying to insert those numbers, and I'm updating the dp of them. Total length means that, like, see, currently I have I, right? Currently I have this number which I have made using the set I, like this using this 2 to the power 1th number, like the a1, using a2, and using a4. I have made this number which has 5 digits, and now I am inserting a0 also. So total length is the number of digits that is there in a4, a2, and a1. And since now I'm inserting a0, I need that total length to calculate that remainder. Tejas, I don't have experience in that aspect. Okay, yeah. So essentially, what I just did is that for every ij, for every dpij, I just, like, if that dpij is true, then I just tried inserting every other number which I have not inserted yet. So I just calculated the new remainder and the new mask. Okay, and now I'll reconstruct it. Like, now I'll start at my destination. Like, I'll start at the state of 11110, like 11111 and 0. So I'll start at this state, and I'll backtrack that from where did I come. So my I is 2 to the power nums dot size minus 1, and my j is 0. So if my dp of ij is false, then it is not possible. So I'll return vector of int, and now I have vector of int ans. So this is my final answer. So now, like, while I'm at the state, like, while I means while I is not equal to 0. Okay. So my next I is the parent of ij dot first. Like, the parent of this state can be, let's say, 11011 comma 4 or something. So this is my next I. Like, I have come from this state to this state. So that means that this bit which is there, which is flipped, I have inserted that. So next I is parent of ij dot first. So I have, since I have inserted this bit, that means that I am basically inserting a2 to my vector. Like, this is a0, this is a1, this is a2. So I have inserted a2 to my vector. So to just check that which bit has changed, I just take the XOR of the current mask and the next mask. Like, the current mask is I, right? The current mask is I, and the next mask is this next I. So what I did is that I took the XOR of I and next I. So I XOR next I will give me, like, see here, if I go from 10111 or 11011 to 11111, if I take the XOR of both of them, then I'll get this thing. I'll get one in that position where there is, like, that number which I inserted. So since this is there, and I can just count the number of zeros after that. Like, I can just use the ctz function. Ctz means count trailing zeros. So I'll just use count trailing zeros of this, right, which will give me 2. And that, like, so that's how I'll know that I have inserted a of 2. Okay, so I'll do answer pushback nums of, like, a of ctz of I or next of I. And now I'll just go to my parent state. So j is equal to parent of I dot second, and I equal to, like, parent of I dot first, the old I and j. Okay, and I'll just do the reconstruction. Okay, so actually this problem is, uh, if you don't know how to do DP reconstruction, then this problem is pretty tough for you. So before, if you don't understand this, and if you don't know already that how to do DP reconstruction, then you should learn that first, and then come back to this problem. Okay. So yeah, I'll move on to the next one now, since I have taken too much time on this. So the last problem is your this problem, that you have the same graph as in problem the first problem. Sorry, the question 2 you had, that you have an array. You have an array of numbers. Yes, I'll share a submission link. It will be in the description later after the stream. Okay. So I have an array in the problem D. You are given integer n representing the number of nodes on a graph labeled from 0 to n minus 1. Also an integer array in terms of length and an integer max diff. An undirected edge exists between the nodes I and j if the absolute difference between nums I and nums j is at most maximum max diff. So the problem is the same as the first problem, like as problem B. Just that in this problem there are two differences. The two differences are that in this problem we are not guaranteed that the list is sorted. Like the input list may not be sorted, it may be unsorted, right? And one more thing, there's difference, that we have to print the minimum distance between the two nodes ui and vi. Okay, and if no path exists between the two nodes, then return -1. All right. So what we want to do, like what we want to answer is that, see, what we have here is we have a graph. We have a graph, and basically there is an edge between node I and node j if and only if thus the nums of I, the nums of I minus nums of j is less than equal to the max difference. Right, so this is your uh, condition. Like how do you create that graph? So this graph can have O of n square edges. This graph can actually have O of n square edges. So you cannot actually create this graph because that will give you TLE. Okay, like the n is 10 to the power 5, right? So you actually cannot create this graph explicitly. You have to solve it some other way. Okay, so what you have here is, like, let's take a sample. Okay, let's say you have this graph, that 18342. Okay, you have 18342, and you have the indices 0 3 and 2 4. Like you have these queries, that what is the minimum distance between 0 3 and the minimum distance between 2 and 4. So that's what you have to report. And you can move between two cells, like you can move from here to here if and only if the difference 3 is less than or equal to the max difference. So the max difference here is what, 3. So the max diff is given to be 3. Okay, so now, like let's say you want to move from 0 to 3, like you want to go from this index to this index. So actually you can go there directly. You can go directly from this 1 to this 4. All right, and let's say, like, because the difference is less than equal to 3, and let's say you want to go from 2 to 4, that is the index 2 to the index 4. So also you can go directly because the difference is less than equal to 3. The difference is 1. So the answer is 1 comma 1. So this test case is pretty useless, to be honest. So let's take this one, 5 3 1 9 10. 5 3 1 9 10. Okay, and we want the queries. The queries are 0 1 0 2 2 3 and 4 3. 0 1 0 2 2 3 and 4 3. So this is your queries and you have to answer them. So let's say we have to go from 0 to 1, from 0 to 1, and yeah, the max difference is 2. max diff is equal to 2. So if you want to move from 0 here to here, you can do that in one move. So the distance is 1. Then let's say 0 comma 2, you want to move from 0 to 2. So now of course you cannot move directly from 5 to 1. You cannot move directly, but you can take two moves. Like you can go from here to here and then from here to here, because the difference of these two is 2. So the answer is two moves. Then 2 to 3, like you want to go from this index to this index. So actually you cannot go from here to here, and because this 1 3 and 5, this 1 3 and 5, and then we have 9 and 10. So this is one component and this is another component. You can never go from this to this, because the difference is too much. The difference is 4, right? So you cannot go from here to here, and that's why it is not possible to reach 9 from this one. Like from 2 to 3 it is not possible. So the answer is -1. Similarly from 4 to 3, sorry, like from 4 to 3, like from 9 to 10, you can do it in one move. So the answer is 1 2 -1 and 1. 1 second. Yeah, so okay, so that's how you can answer this test case. Like the answer to this is 1 2 -1 and 1, right? So first idea here is like how to solve this. Now if you solve the second question with me, I explained to you that how is sorted thing actually helpful to us. Like since the array in this case is sorted, we can actually divide this array into multiple components which are independent. Like I can move between this one component, and also I can move between different, I cannot move between two different components. So that's why sorting this array is actually beneficial for me. Like in this case the array was sorted, right? So that actually helped me very much to analyze. So in this problem also, I'll try to sort this array. Like I'll try to sort the input array, and I'll also keep track that where are the elements going. Like for example, I have this array that 5 3 1 9 10, right? So we have 5 3 1 9 10, and our indexes also. So this is index 0, index 1, index 2, index 3, and index 4. If I sort this array, okay, it will become 1 3 5 9 and 10, and the indices are 2 1 0 3 4, right? After sorting, this is what it becomes. After sorting, it becomes like this, right? So let's say now you have a sorted array and you want to move from one index to another index. Like let's say your query is what? Your query is, let's say, 0 comma 2. So let's say you want to move from here to here, or equivalently you can say that you want to move from here to here, because the graph is undirected, so it doesn't matter. So let's say that you want to move from this 2 to this 0. So how will you do that? Like actually you can just try to jump from this 1 to 5. Like if you try to jump from this 1 to 5 directly, you cannot do that, because your gap is too much. Your max difference is 2, right? So you cannot jump there directly, but you can jump to here in one move, and you can jump to here in one move. So now you might be asking that what is the, like, why are you sorting this vector? Okay, so actually the thing is that after sorting, like let's say you have this sorted vector. Let's say this is your sorted vector. Just 1 minute. Yeah, so let's say you have this solid vector and you want to travel from here to here. Okay. And let's say you want to calculate the minimum number of moves to do that. So how will you do that? How will you do that? What you can actually do is from this cell, from this cell, just travel the farthest right that you can go. Like let's say for example, my max difference, my max diff is equal to 4. Okay. And I have the numbers, like let's say 7 is written here, 8 is here, then 8 is also here, then 10 is here, and 10 is here, and here is 13, here is 14, and here is 17. Okay. And you want to reach from 7 to 17, and your max difference is 4. Like the maximum jump that you can take is 4. So how will you actually move? So my point is that when you start at 7, you start at 7, then you will greedily move the furthest right that you can go. Like from 7 you can greedily move to the furthest right, so you'll move to 10. Okay. Then from 10 you can again go to 14. That is the furthest you can go in one move. And from 14 you will go to 17. Okay. So this is what the optimal strategy is, that going to the furthest right, going as far as right as you can, that is the optimal way to do this. Okay. So in one move, what you can do is, what you will do what you will do is go to the furthest right, like provided that it does not exceed. Like for example, if there is, let's say, an 18 here. Okay. So what you would do is, from this 7 go to this 10, then from this 10 you go to this 14, right? And then from this 14 you go to 18, but you won't do that, right? Because you want to just go to 17. So except for the last one you will move the furthest you can. Okay. Like from 7 you will go to 10, from 10 you will go to 14, and from 14 you will go to 17. Okay. So this strategy actually works. This strategy is the optimal strategy that you can apply. So let's say you have a query, like let's say you got a query that you want to start at 7 and you want to end up at 17, right? So in that case, what you would do is that you would keep a pointer here. Like let's say your p1 is here, or let's say your a is here and your b is here. So now from a, how will you find out that till where can you go in one move? Till where can you go? How will you find out? You can simply do a binary search on this array. Okay. And find out the value of a plus max difference. Like basically from a you can go till a plus max difference. That is the rightmost you can go. So since max difference is 11, you can go till 11, but there's no 11. So before that you will go till 10. So you will find the last number which is less than equal to a plus max difference. So you will find the last x which is less than equal to a plus max difference, and that's where you can go in one move. All right. So simply you will go there, like using binary search you will find that, and simply you will go there. Sorry, not here. You will simply go this 10, right? Then from this 10 again you will find out that what is the maximum we can go. So 10 plus 4 is 14. So you will find out the maximum value of x less than equal to 14. So it is this one. You will go to 14. Now again from 14 you will calculate, you will do binary search, and you will go to 18. Like you will find out that it is 18, right? But of course you won't go there. You will go to 17. Like in one move, if you can go to 18, then of course in one move you can go to 17 as well. So at some point, if you just cross B, then stop right there, and that will be your answer. So let's say like when you're at 14 and you cross this B, so you have taken three moves. This one move, another move, and one more move. So the answer is three. But for this approach, like the approach is correct. The approach is correct in terms of wrong answer. Like if you do this, then wrong answer will not come. Okay. But the word TLE will come on some test cases. Why? Because the complexity of this approach is very large. Like basically the number of moves. It is basically O of number of moves. O of number of moves into log n actually. Into log n. And maybe even number of moves can be very large also. Right? So that's why this will give TLE. So we have to do better. Right? So from actually why did I tell you this? I told you this approach to show you that it is optimal to move to the furthest right that you can. Like from this point, you will move to 10 directly, and then you will move to 14, and then you will move to 18. Right? So in three moves you can do that. So basically, from this 7, you will store that in one move you can reach this 10. Then from this 10, in one move you can reach this 14. And from this 14, in one move, you can reach this 18. Alright. So now what to do? Like how to optimize this? We can actually store that. Okay, let's say this is my sorted array, right? I have sorted into this array and this is my array. So let's even just copy this 7, 8, 8, 10, 10, 13, 14, 17, 18. 7, 8, 8, 10, 10, 13, 14, 17, 18. 10, 13, 14, 17, and 18. Okay. So we have this in like I'll index this 0, 1, 2, 3, 4, 5, 6, 7, 8. All right. So what I'll do is I'll store that for each index, what is the furthest I can go? Like if I start at some index, let's say I start at 0. If I am at 0, then what is the rightmost that I can go? Okay. So from this 7, I can go till this 10. Right. So I'll store a 4 here. Like I can go to this index 4, right? So I'll store 4 here. Then from this 8, I can go to 4 only. So I'll store 4 here. Then also I'll store 4 here. Then from this 10, in one move, I can go to up to 14. So I'll store a 6 here, then a 6 here. Then from 13, I can go till 17. So I'll store 7 here. From 14, I can go till 18. So I'll store an 8 here. From 17, I will go till 18. So I'll store an 8 here. And from 18, I can go till 18 only. So I'll store an 8 here. So basically, in one move, you can actually traverse this. Like if you start at this point, if you start at 0, then you can reach till 4. If you start at 1, then you can reach till 4, and so on. In one move, you can do this, right? But now, what about in two moves? Like in two moves, till where can you reach? Let's say I want to find out that if I start from 0, then in two moves, where can I reach? So that's just so doing two moves is equivalent to doing one move and then one move, right? So from 0, if I do one move, so I'll go to this 4. Like from 0, if I do one move, I'll reach this 4. And if at 4, I'll do one more move, I'll reach 6. So basically, this is one move. Now for two moves, I can store that where will I reach? Like where will I reach? Like basically, um, using two moves, if I start at 0, I'll reach at 6. Why? Because the first move is 4, and from 4, if I do one move, then I'll reach 6. So therefore, if I do two moves from 0, I can reach at most 6. Okay. Then from 1, if I do two moves, then also I'll reach 6, then 6. Then from 3, if I do two moves, then I'll reach till 8. Okay. Because I'll reach 6, then from 6 I'll reach 8. Then if I do two moves from 4, then also I'll reach 8. If I do two moves from 7, then also 8, and 8 all along. Okay. So in two moves, if you start at 0, 1, or 2, you can reach till 6. And if you start at like 3, or like in these indices, if you start in two moves, you can reach till the end also, right? So that's what you can store. Now what you'll store is, in 4 moves, till where can I go? In 4 moves, if I start at this index, till where can I go? So to calculate that, simply you are starting at 0, and doing 4 moves is same as doing 2 moves and then 2 moves, right? So from 0, if you do 2 moves, you can reach 6, and from 6, if you do 2 moves, you can reach till 8. So if you start at 0 and you do 2 moves, then you can reach 8, right? And so on, you will fill on for the rest of the elements. So this table that you can actually see that we are making, like we are simply storing that after doing 2 to the power I moves, after doing 2 to the power I moves, where can I reach? Like if I am currently, or sorry, let's say I am currently at the position number j. Okay, if I do 2 to the power I moves, then till where can I reach? Till where can I reach? Right? This is my store. Like that's what I'm storing right here. Okay. So now let's say that I want to calculate that if I am at some position j, like let's say I am at some position number j, and I already have all is power of 2. Like I have that after doing one move, where can I reach? After doing two moves, where can I reach? After doing four moves, where can I reach? So I already have these values for all the powers of 2. So let's say that I know that currently I am at j, and I ask you that after doing 30 moves, after doing 30 moves, where can I reach? Where can I reach? Okay. Then what you can just do is that, like 30 mein there is 16, right? You're gonna 30 as 16 plus 8 plus 4 plus 2, right? So what you will just do is that from j, you will first do 16 moves, and you know that where you will end up, because that you have stored. Because 16 is the power of 2, you know that if you go to 16 moves, where will you end up? Then from that position, let's say from j you went to k after 16 moves, then after 8 more moves, you have come to l, from k to l. Then after 4 more moves, you have come to uh, let's say h, for example. And if you do 2 more moves, then let's say you go to I. So at the end, you have done 30 moves from j, and you have reached the ith position. And that's how efficiently, like in log n amount of time, in just log n time, you can find out that starting at some position, where can you reach? Till where can you reach? Right? So actually, this is called binary lifting. Like some of you might know it, but some of you might not. It is called binary lifting. Binary lifting. Okay. That you just store that from starting current index till where can you go using 2 to the power I moves. 2 to the power I moves, till where can you go? Right? And now what you will just do is that, okay, now the problem of R is not yet solved. Like we want to solve the problem that if I start at this position, like if I start at this position j, let's say, and I want to reach this k, right? Or let's say A and B. Like if I start at A, if I start at the position number A and I want to end up at position number B, so how many moves will I take? How many moves? Right? So actually to do that, what I can do is, see, the upper limit is 10 to the power 5, right? Or the upper limit is n. Like if we are able to reach B, then of course we can reach B in at most n moves, like less than n moves. In fact, we can reach B in less than n moves. So the upper limit is actually n. And what is n? N is up to 10 to the power 5, right? So 10 to the power 5 means approximately 2 to the power of 30. Not 30, wait. Um, 2 to the power 10 is 10 to the power 3, right? So 10 to the power 5 is approximately 2 to the power 16. Okay. So what I'm saying is that at most in 2 to the power 16 or 2 to the power 17 moves, we can definitely reach B, right? And if even more than that, like even if after doing 2 to the power 17 moves, we are not reaching B, then we will not be able to reach B. Like for example, if I have 1 here and an 8 here, okay, and the maximum jump is my 3, then of course I cannot even move from here to here. So after doing one move, I will remain here. After doing two also, I remain here. So in my table, after doing 2 to the power 17 moves also, I will remain here only. That will be stored. So even after doing 2 to the power 17 moves, even if you can't reach till B, then you will print just -1. B is unreachable. Okay. And otherwise what you will do is just iterate from 17 to 0. Okay, hear me out. Just iterate from 17 to 0. So like for example, what you will do is you will check. Okay, so currently you are at A. Currently you are at A, right? Currently you are at A and you want to go till B. And you want to answer the question that how many moves will you take? How many moves will you take? So to answer this, what you will do is you will just iterate from 17 to 0. Iterate down. Okay. So let's say you will iterate from I from 17 down to 0. Right. So um, let's say currently you are at 2 to the power I. So if after making 2 to the power I moves, like after making 2 to the power I moves, if you are still behind B, like the currently A is behind B, right? So if after doing 2 to the power I moves, if you are, let's say you go till here, if you reach till here, then of course your answer is at least 2 to the power I. So what you will do is you will add answer plus equals to 2 to the power I, and then you will move your A to here. You will move A to here, and then you will do this with the new A. Like you will keep iterating downwards. So first it is like first you will check for 17. Like what you will check? First you will check that after doing 2 to the power 17 moves, am I still behind B? Okay, am I still behind B? And if yes, then you will go there. Like you will perform 2 to the power 17 moves and you will go there. All right, and you will add your answer to 2 to the power I or 2 to the power 17. So currently your answer is 2 to the power 17, and currently you have moved 2 to the power 17 moves. Then let's say your I is 16 now. Now let's say you want to figure out that whether or not you can um, move to, like whether or not if you add one more 2 to the power 16, like if you do one more 2 to the power 16 moves, then where will you reach? So even then, if you reach behind b, like even then if you are behind b, then of course you will add 2 to the power 16 also. So the answer is at least this much. So you will do this for all, like okay. And if you are reaching, like after doing 2 to the power 16 moves, if you are reaching after b, like if you are reaching ahead of b, that means you have overshot and you don't need to make that many moves. So you won't add 2 to the power 16 to your answer, and you will simply stay there. Then you will check for 15, that if after doing 2 to the power 15 moves, if you do 2 to the power 15 moves, then where will you reach? So let's say you reach till here. So you will add 2 to the power 15 to your answer. And you will keep doing this until you reach I equal to 1 or I equal to 0. So you will have done is that you will have reached one step before B. Just one step before B. And finally, like since you are trying that you are always behind B, like if you are reaching behind B, then only you are doing the moves. So finally, what you will be left with is that you will be one step before B, and then you will just do one more move. Like you will just do answer plus plus. Prince is saying that we need minimum moves, so we should start from 0. No, like the sense of starting from 2 to the power 17 is that we are checking that is the answer at least 2 to the power 17 or not. See, let's say that from A to B, to go from A to B, I need, let's say I need 26 moves. Assume this. Let's say I need 26 moves to move from A to B. Okay. So what I'm doing is I'm iterating from 17 down to 0. Okay. So now I'm checking that if I start from A, if I start from A and I do 2 to the power 17 moves, so where will I reach? So of course I will reach after this B, right? So therefore I will not add 2 to the power 17 into my answer. Similarly, if I reach, like if I do 2 to the power 16 moves, I am at A, and if I do 2 to the power 16 moves, then where will I reach? So of course I'll reach after this B, because 2 to the power 16 is much greater than 26, right? So this will keep happening until 2 to the power 5, or even with 2 to the power 5. If I check that if I do 2 to the power 5 moves, then where will I reach? So the answer to that will be after this B. Like I will overshoot this B. So my answer will not be 2 to the power 5. But if I try to make 2 to the power 4 moves, if I try to make 2 to the power 4 moves, then I will be remaining before this B. Like I will remain before B. So I will make those moves. Like I will move A to here. I'll move A to here, and I'll add this to my answer. Like I have already made 2 to the power 4 moves. All right. And now, like, so essentially what, like I've already made 16 moves, right? I've already made 16 moves. So I need 10 more moves to go from the current position to B. So now if I check that if I do 2 to the power 3 more moves, that is 8 more moves, where will I be? So again I will be before B. So again I will move there, and I'll add it to my answer. So 2 to the power 3. And now I am remaining with 2 more moves. Now if I do 2 more moves, then I will actually reach B. So I won't do that. Like I'm trying to stay before B. So if I do 2 more moves, I'll reach B. So okay, wait. 2 to the power 3 are, we just did 2 to the power 3. So we'll check 2 to the power 2. So since 2 to the power 2, if after doing 2 to the power 2 moves, we'll overshoot B, right? Currently we are here. After doing 2 to the power 2 moves, we'll overshoot B. So we won't do that. And after doing 2 to the power 1 moves, 2 to the power 1 moves, we'll reach B. So actually we won't do that because we want to stay behind B. Okay. And after doing 2 to the power 0 moves, like one more move if we do, then again it will stay behind B. So we'll do that. So now we have reached one step before B. Okay, and our answer is currently this thing, and we'll need to make one more move in order to reach B exactly. So I'll add 1 to this, and the final answer is 16 plus 8 plus 1 plus 1, which is 26, which is what we had here, the number of moves. And actually, if you don't get this part, like why are we iterating from 17 to 0 down to 0? Like why are we iterating from 17 down to 0? Actually, what you can just do, see, I showed you that if I start at J, if I start at J and I make K moves, if I start at J and I make K moves, then where can I reach? Where can I reach? I showed you how to answer this question, right? Like I showed you that if I start at J and I want to make 30 moves, then where will I reach? So to answer that, we can simply use binary lifting, and we can answer it in log n time. So actually, what you can do now is do a BS on the answer. Like what you will do is based on the answer. Like what I'm saying is that just try doing some moves, and if you overshoot that, then you will simply try less number of moves, and so on. So you will find out that sweet spot, that what is the minimum number of moves that you have to do. So this is one more method. This is like you can use this one more method. This is method 2, that um, you can do based on the answer, and the check function will be that after doing mid number of moves, if you overshoot B or if you land up at B, then you can possibly make less number of moves. So you will make high equals to mid, and if you are still behind B, then you will set low equals to mid plus 1. Like you will have to try more number of moves. So this will work in O of n log square n. Sorry, O of log square n, I mean per query. Because this binary search will take O of log n. And to find out that after these many moves where we will end up, that will also take O of log n. So this is O of log square n. And yeah, that will work. But my approach is O of log n because I'm trying iteratively to just do that power of 2 moves. But if you already don't know about this trick, then I think it is pretty tough to understand. Like you can search about it here, like LCA using binary lifting. If you know this, then this is pretty easy. Like in this also, we do the same thing. Okay, like for int I equal to L, I greater than equal to 0, I minus minus. So they are doing the same thing here. All right. So like if you already don't know about binary lifting, then I like recommend you that you should learn about it to solve this problem. Like I don't think there's another way. There is another way to solve this problem except for binary lifting. So this is your algorithm. All right, and I show the code. So I have vector of pair of int comma int v. So I have taken the input into a vector of pair so that I can sort it, right? So I'll do v dot pushback make pair num psi comma I, and then I sort this, and then I store the position of all the numbers, like all the indices. I store the position of them. So for position of vi dot second is equal to I. All right. Then I have this vector called next. So next means that if I am at the position number I, then where can I go after one move? Okay. So for every move, for every position, what I'll find is upper bound of v dot first plus max difference. I'll find out the upper bound of v dot first plus max difference in my vector, and basically I cannot go there, but I can go till the previous one of that. So my index will be it minus without begin -1. So that's what I can go to in one move. And now I'll calculate this lift vector. Like I'll calculate this lift table. Like I have a 25 by n table, which is storing that basically lift of ij. Lift of ij is storing that after 2 to the power I moves, if I make on this j, then where will I reach? So basically lift of ij means I need to make 2 to the power I moves from j. So what I can just simply do is do 2 to the power I minus 1 moves on whatever I reach on making 2 to the power I minus 1 moves. So I just do 2 to the power I minus 1 moves 2 times. So this is your lift I minus 1 I minus 1 j, right? And also lift 0 is just next. Like after doing one move, where do we reach? We already calculated that in the next vector. So my lift of 0 is just next, and from lift of 1 onwards we can calculate it using lift of the previous one, right? And to handle the queries, this is my a and b. If a is equal to b, then the answer is 0. If a is greater than b, and yeah, first I do that a is equal to pos of query of 1. So I do that if they are asking for some node, then first I'll find that node. So my a is my index. My a is the index in my sorted array. Okay, and same with b. And if they are same, then the answer is 0. If a is greater than b, then I'll swap a and b. So now a is less than b, right? Now I'll check that if lift of 24 comma a, that is if I do 2 to the power 24 moves from a, and if that is still less than b, then I can never reach b. So answer was like -1 and continue. Now I have my answer equals to 0. So I iterate from 24 down to 0. If lift of I comma a is less than b, like if we can perform these number of moves and still be behind b, then we'll perform them. So this plus equals to 2 to the power I. Okay, and I'll also perform that move. So a is equal to lift of I comma a. And so yeah, I'll do this for all I from 24 down to 0. And finally, I will push back dist plus 1, because by now we are just behind b. So we need to make one more move in order to reach b. So the answer is distance plus 1. And we return answer. And like this distance plus 1, this thing is actually analogous to what we do in the LCA. Like in the LCA, we are doing binary lifting, right? And then finally we read, like finally we return one more ancestor. So that's why I'm doing like plus 1 here. This is the same thing as the binary lifting in my LCA. Yeah. So Prince has understood. And like I think if you already know about binary lifting, then I think you should understand this. So if you don't know about it already, then then you should learn it and then come back to this video. And then if you have a doubt, then you can comment on this YouTube video. All right. So anyways, this was roll number 4. And yeah, Sultan is asking, I have 3 years building Zcash game steps. Often I feel stuck and I don't understand anything. Any advice for me? So Sultan, are you asking for like CP, or or are you asking in terms of CP DSA, or like C++ development? Like what are you asking? Like in DSA and CP, the C++ knowledge is not necessary. Like I think more than your knowledge in C++, your logic and reasoning skills are more like crucial. So that doesn't matter that you know so much C++ and you have done so much coding in C++. if you have not done CP or DSA and you don't know algorithms and data structures, then I think like you should learn that. Like if you have not tried learning it, then like not even learning, I think it is more about practicing. Like CP and DSA is all about practicing different problems and many problems and getting the hang of it and like building an intuition, right? That is the only way to do it. Like I also personally have solved many problems, and that's why I am at the current level where I am. Like as you can see that on the CF website, I have solved more than 1300 problems. All right, so it is all about problem solving. And for development, actually, I don't know. Like I think you would know better than me, because I haven't done development at all, and you have done for 3 years. So you would know better than me. I can't comment on that. But for CP and DSA, I am telling you that the practice is the only source of learning. All right. Yeah. So okay. So I think now that we have done all the four problems, I think I can end the PCD. And thank you, Prince, for the thanks. I mean, you are welcome. Okay. So, anyways, I'll take your leave now, and bye bye, everyone.